Well, I'm Joel David Hampkins from New York, and it's my pleasure to chair this session and introduce the speaker. There's only one talk in this session, and it's Arno Pauly from Cambridge, and he's going to speak about connecting topological dimension theory and recursion theory.
Thank you very much. So this will be all worked together with my course Kiara-san, who is now at Berkeley, was just before. And the idea of the talk in a nutshell is that we can introduce a particular notion, the point degree spectrum of a space, which is then linking descriptive set theory, in particular in flavors like aspects of the dimension theory and so on, computable analysis in the style of Klaus Weyrauch, and the recursion theory as in structures like the Turing degrees, the Medvedev degrees, and so on. While the concept itself is really a very simple and straightforward concept, we can then use that to translate between these two. We can then go back and forth between these realms and use and actually solve some open questions by using the techniques from the different stuff. My assumption is that the audience here will probably be most familiar with and interested in the descriptive set theory part. So I'm going to start with a particular question from there, which I can then show you the answer to. So let's restrict ourselves to complete metric spaces for now. It's not necessary for anything else to work. And we're calling these we're calling them piecewise homeomorphic if we can split both spaces into countably many parts, and then the matching parts are homeomorphic.
You don't insist that they're Borel or anything like that, the pieces?
Well, it turns out that there are such pieces if and only if there are, if you can make the pieces to be pi 0, 2. So kind of if you don't like complicated pieces, you don't have to use them, but it wouldn't help you anyway. Yeah. And then it turns out that the small inductive dimension of the space being a well-defined ordinal number is just the same thing as the space being. This is true for uncountable spaces, of course. If you have finite or just countable spaces, this is a rather boring thing. So for uncountable spaces, they're going to be countably dimensional if and only if they're piecewise homeomorphic to Cantor space. So we have kind of at least two uncountable classes for this homomorphism type, and it has been an open question for quite a while, well, whether there are more than the straightforward ones. So, for example, we clearly have Cantor space and the Hilbert cube. But both Jane and Rogers, and then more recently Luca Mataros, Philip Schlicht, and Victor Silvano are some more. This is, for example, related to the question of there being certain Banach algebras which are not linearly isometric. This is related to the structure of watch degrees on these spaces and so on. And yeah, that's a question I'm going to answer. The contribution of computable I'm not going to say that. To this work is mostly the notion of a represented space, which is sort of the general setting we're using to talk about computability, which will then bring recursion theory into play. That's really just a partial surjection from bare space onto some set X. We then have a notion of a function on bare space realizing a function between represented spaces. It just makes this diagram here commute. And then we can call functions between represented spaces continuous or computable if they have some realizer having that property. Now, I should probably justify that the notion of continuity here really matches the notion of continuity on the spaces we're interested in. And for that, I'm going to introduce the notion of a computable metric space. Or actually, for this talk, I really need the weaker notion of an effective metric space. That's really just a metric space with some fixed dense sequence in it. And then we can define a representation of this. There's some, the idea here is supposed to be a partial function from bare space to M, which essentially maps a sequence coding Cauchy sequence, which is converging reasonably fast, with the point it is converging to. And that sort of this representation really means that the represented space and the metric space we started with are the same object in a sense, as justified by the theorem of Klaus-Weyrauch, that the continuity notions we have in these two settings are the same notions, so it's really the concept that it should be. In that context, it has been a question raised by Borel and Richards, I think about 30 years ago. They had noticed that each real number has a some code which has kind of the least complexity of all codes for that particular number. They then asked the question, well, is that true for all computable metric spaces? Will we always have least codes? Joe Miller showed about 10 years ago that this is false for the Hilbert cube, which then raised the question, can we describe clearly in which spaces all points have Turing degrees and in which spaces they're weird, they're more complicated points which do not have Turing degrees? That's also going to be a question I'm going to answer. So we can then almost define the point degree spectrum now with one final notion, that is the notion of Medvedev reducibility. That's defined between subsets of a bare space, and we're just saying that A is Medvedev reducible to B if there is some computable function defined on the set B, which is going into the set A. This, of course, is only a really interesting notion if these sets do not have if A does not have any computable points in it, because then it's hard to actually get a function into that space. So we need something inside B in order to be powerful enough to compute something inside A.
Does it have to be onto?
No.
You said into, but
it just has to be a well-defined function. So if the set A has, for example, if A contains some computable point and B is not empty, then A is Medvedev reducible to B, because we can just pick the constant function taking that point and we're done. Right. So we are taking a represented space, and then we're looking at all the sets of sequences inside bare space, which are names for the same object inside that represented space X. And we do not care about the precise sets because they are not invariant under reasonable transformation of the space, but we care about the Medvedev degrees of these points. Now we can understand the Turing degrees to be a substructure of the degrees defined at the top in the straightforward way by identifying the sequence by the set just containing that particular sequence. In particular, the question for which spaces it is true that all points have Turing degrees is essentially just asking for which spaces is the spectrum contained in the Turing degrees. For example, for bare space and the real numbers, we get precisely the Turing degrees. For the Hilbert cube, we get a structure introduced by Joe Miller as the continuous degrees, and that's more or less how he defines them. A notion which has been around for much longer is the enumeration degrees, which you can consider as just the point degree spectrum of the power set of the natural numbers equipped with this called topology. So how does this notion work together with interesting stuff? So we find that the spectrum of X is going to be a subset of the spectrum to the spectrum of some space Y. If we can partition X into pieces which are all computably homomorphic to some subspace of the second space, we can then kind of translate that into a form where we're actually talking about just being homomorphic and get rid of the computably if we just relativize with respect to some particular Turing degree, and we can resolve the issue that we could reuse the subspaces in the first theorem by just making sure that that we've got sufficiently many subspaces, because then we can use the Cantor argument below. So we see that we can actually characterize the pieces homomorphism types up to multiplication with integers by looking at the point degree spectrum up to relativization with respect to some particular point. That gives us the answer to the question by Borel and Richards. A space is a computable metric space is going to have Turing degrees relative to some fixed one if and only if it has countable dimension. And the kind of harder question now becomes whether we can find some polar space which has point degree spectrum which is somewhere in between the Turing degrees and the continuous degrees, and that has to be true relative to each fixed oracle. So well, there isn't just one, there are actually quite a lot of them, and well, we can both make a chain, and we can also have incomparable ones. I'm not going to be, I will not mention how to prove part 2 at all. I'm going to show you an explicit construction of one example for the first, and then wave my hands a little bit to argue how one can generalize that to get more of them. So, to build the space using a slightly complicated notion from recursion theory and omega left CEA operator, the idea is that we have some computable function. We are building a sequence in the Hilbert cube by starting with some finite prefix of that sequence. We are then taking the lim sup over all of the things or functions generating there when given one more parameter. that's telling us what the next step is, and then we're going to use that lim soup and plug that back into the function to get to have more. Since computing a lim soup is more or less just as hard as computing one Turing jump, kind of computing the nth entry here will need an iteration of the jump. We can enumerate these guys in a sensible way, and then we can define a subspace of the integers times Cantor space times the Hilbert cube, essentially as the graph of a universal omega left CA operator that is a Cantor space, more or less because you can always, well, kind of you can show that the graph is a pi 0, 0, 1 set, and then it's Polish as a subspace of the space it's defined in, and it has precisely the aspects that we are looking for. Now, stuff which is looking like the space has shown up before. That's just a side note. So it has the same piece of homomorphism type as the Rubin-Shori wash, totally disconnected, strongly infinite dimensional space, and it has also the same type as Roman Pol's counter example to the problem posed by the guy who's named there. So it's it was quite surprising just to see that kind of despite the fact that if you compare the constructions, you can't see it at all. If you work a bit on it, it's actually kind of not just a particular weird space, but a standard weird space, so to say. How to see that this is true, and how to see that we can build so many different constructions like this. Well, we can look at the question given, well, fix some particular point, and then look at both all elements in Cantor space which are powerful enough to compute that point, meaning to compute some name of that particular point, and then look at all sequences in Cantor space you can compute if you just have some name for that point given, but you don't know which one, and you have to be able to deal with the ambiguity. Well, if your point is living in Cantor space, then you're just looking at the kind of all points during all sequences during above it, all sequences during below it, and these sets of course just meet in that particular point. Now in the Hilbert cube you can have points which are in a sense which are really hard to compute but are really useless in computing sequences in Cantor space, essentially because a big deal of the complexity is built into the question whether a particular component is a rational number. Since you can't decide whether a particular component is a rational number, you can't figure that out, and you can use that to actually make the gap as big as you want. In this particular space, we can construct from the operator. We have that we can have gaps, but gaps can't. Well, each gap can be crossed by using the omega iteration of the jump. So there's always something inside Cantor space which you can compute from a point, and if you take the omega iteration of the Turing jump of that point, you can, of that sequence in Cantor space, you can compute that point. And by actually doing just a small modification of that construction, one can show that for any regular countable ordinal, you can make a space which has some gaps of that length, but no smaller ones. Since the length of such a gap is being preserved by piecewise homeomorphism, that then gives us all these hierarchy of spaces which have all the different complexities. The details are all up on the archive in case anyone wants to have a look. Just a few mentions of some other nice things one can do with that. We can, for example, construct a particular non-degenerate continuum where there aren't any points which have Turing degrees in the first place. This, of course, is only a property up to computably piecewise homomorphisms. If you take a piecewise homomorphism which is just using a very strong oracle, you can always make some points look like Turing degrees. So we can ask whether we can get something stronger. That's more or less rediscovering a theorem by Turing, I think from 1907, something like that. So if and only if the continuum hypothesis happens to be true, then there is an infinite dimensional space which you can pick as a subspace of the Hilbert cube, such that any countably dimensional subspace already is countable.
Sorry, is it uncountably? It's an uncountably dimensional space. So X is uncountable.
Yes. Well, yeah. So the
No. It's infinite. Oh, well, infinite dimensional has to be.
Yeah. So the property for X means essentially that this process of taking the boundaries of really small neighborhoods around points and then working on these boundaries that will not get you towards the empty set, no matter how often you're for iteration over all countable ordinals. Yeah, so kind of X has to be a rather big space, but it kind of all subspaces either have we can only have two cases. Either they're countable, meaning that the dimension will actually be zero, or that the dimension is not even any countable ordinal whatsoever. Since the paper is written in French, I've only got a vague idea of what it's saying. I think the construction is similar to the one we used, but I think that may actually be a simpler one to grasp. So, well, you can start with asking the question whether you can pick some chain in the Turing degree such that all Turing degrees are below something inside that chain. Since the chain can be since the number of Turing degrees is the cardinality of the continuum, and the maximum length of some chain is just and since there are only countably many Turing degrees between any particular one, this can only be true if the continuum hypothesis happens to be true as well. And out of any such collection of Turing degrees, one can then construct a the space X with that particular property. And for the final minutes, let me also show that we can start with work in this descriptive set theory and get results in recursion theory. So here we are now going slightly beyond just the complete metric spaces, and are actually looking at the reals with the lower topology. That's a quasi-Polish space, but not a Polish one. And one can essentially looking at the order dimension of the specialization order shows that the more kind of that if you're using the nth product of that space, it's simpler space up to piecewise homomorphism and uses the nth plus one product. Now the degree spectrum of the lower reals has been studied in recursion theory under the name of semi-recursive sets for a while. And then this one here gives us the consequence that if you take n semi-recursive degrees, takes a product as an enumeration degree, you get less stuff than if you would just take one more semi-recursive one. I'm not that sure how interested people in recursion theory are in a result like that, but it's sort of that does not seem to be known, and it's not something where people would actually know how to prove it in a using more recursion theoretic ways. Also seems to be a useful application of the concept. So, believing the watch, I should, as I said, point you for more details to the paper on the archive or to questions you may ask now. Thank you very much for the attention.
Yeah, this is probably not really related to computability, but could you in ZFC find a continuum such that every countable dimensional subset is of size less than continuum? This is not, or is this could be independent?
So,
because you have one under CH.
Yeah.
Because there less than continuum is the same as countable. But maybe in ZFC you have such a thing, but you replace, if you replace countable with less than C. I don't know,
yeah.
but I think it's, well, topologically it's an interesting question.
Yeah, kind of the way we've used it, unfortunately, does not do that. I mean,
yeah, I'm sure.
I mean, it would be quite nice to say, well, just take a particular chain and then look at all of the things which actually be below that chain to get a construction. But I think
it's also, I don't know, it's probably not true that there is usually called a scale, cofinal and linearly ordered, well ordered, it's the same. I'm sure there is no such thing in ZFC, the Turing degrees. But
is that a cardinal characteristic, though? This smallest
that's another question.
Subset of the Turing degrees? Are there any other questions for the speaker?
I'm just wondering, I know in the definition of various types of infinite dimensional spaces, so I know that you went through with what you would call the successor stage, where a space has dimension n if exists a point such that so how do you what do you say to get past the limit stage? Is this this is a cardinal valued quantity or an ordinal
No,
valued?
well, it is so a space has the dimension at most alpha, where alpha is some ordinal.
So it's an ordinal.
If well, if each point has arbitrarily well,
Right.
so if each point I think has
A neighborhood base
Yeah.
whose
Right.
boundary has smaller
has
dimensions.
has
smaller, right, so
just
this
That's
takes
the
care of the limits.
inductive, the inductive.
So this takes
Right.
care of the limit stage automatically by that. So in
Yeah,
other words,
sure.
so when you say countable here, you don't just mean dimension omega. This includes dimension omega plus omega.
Yeah.
or
No, that's all countable.
I see. And there are
Yeah.
interesting spaces of dimension omega plus omega that are not.
But there are
There are
spaces
spaces.
which don't
Yeah.
have
Yeah.
dimension, which has to be a countable ordinal. I mean, they don't, that,
and I would be highly surprised if you come across a space of dimension greater than omega, which is not infinite dimensional, without setting out to look for such a space.
Yeah.
Um,
Interesting was the wrong word.
Yeah. But kind of
Just Hausdorff spaces.
for each countable ordinal, there's a complete geometric space of that particular one.
Any other questions?